Everything around you began in a single, unimaginable moment. This is the story of the Big Bang, the explosive origin of our entire universe. We are going to trace its faint echoes across the cosmos and explore the profound questions that still baffle the brightest minds. By the end, you will understand not just what science has uncovered, but why the remaining mysteries are the most thrilling part of the story. We will investigate why the universe is not what it should be, and what existed before time began. This journey reveals how the largest structures in existence grew from the tiniest quantum seeds. What does it truly mean that we are made from the echoes of that first explosion? That infinitely dense point contained everything we know, all of space and time, packed into a volume smaller than a single atom. In an incomprehensible flash, it began to expand, not into empty space, but creating space itself as it grew. This is the heart of the Big Bang Theory, our best story for the origin of everything. It tells us our universe was born from an incredibly hot, dense state approximately 13.8 billion years ago and has been cooling and expanding ever since. But how did scientists even arrive at this staggering idea? The story starts not with a bang, but with a slow, steady drift. In the 1920s, astronomer Edwin Hubble noticed that distant galaxies were all moving away from us, their light stretched into redder wavelengths. It was as if the fabric of the cosmos was stretching, carrying the galaxies apart. Then, in the 1960s, two engineers accidentally stumbled upon a constant, faint hiss of microwave radiation coming from every direction in the sky. This cosmic microwave background is the cooled-down afterglow of the Big Bang's first fireball, the oldest light in the universe. It was the smoking gun. Decades before these discoveries, a Belgian priest and physicist named Georges Lemaitre had already proposed the radical idea. He called it the hypothesis of the primeval atom, suggesting the universe expanded from a single, dense point. The theory hinges on a few profound concepts. The starting point is a singularity, a condition where the known laws of physics break down, a point of infinite density. Then came inflation, a brief period of unimaginably rapid expansion when the universe ballooned from subatomic size to something much larger in a tiny fraction of a second. To visualize the expansion that followed, think of the surface of a balloon. As you inflate it, every dot drawn on that surface moves away from every other dot. There is no center on the surface, just an overall stretching. Our universe is like that, but in 3 dimensions. Galaxies are carried along as space itself expands. So we have a compelling narrative from a hot, dense beginning to the vast cosmos we see today. Yet this brilliant explanation immediately raises a deeper, more difficult question. If the Big Bang describes the evolution of the universe from that first moment, what was the trigger? What set the whole cosmic story in motion? To answer that, we must journey back to the very first instance, to a time so early our current physics cannot fully describe it. This faint echo is the cosmic microwave background, a whisper of radiation that has been traveling for almost the entire history of the universe. It is the cooled and stretched remnant of the universe's first light, a direct relic from its fiery infancy. Its discovery was one of the greatest accidents in scientific history. In the 1960s, 2 radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent, annoying hiss in their giant horn antenna. They assumed it was mere static, perhaps from pigeon droppings inside the antenna, but no amount of cleaning could eliminate it. The signal was coming from every direction in the sky, a constant, uniform whisper. They had, without realizing it, stumbled upon the afterglow of the Big Bang itself. This cosmic microwave background provided the strongest possible evidence for the theory, a universal fossil imprinted on the sky. This radiation allows us to see the universe as it was when it was only 380,000 years old. Before that moment, the cosmos was a hot, opaque plasma, a dense fog of particles and light. As it expanded and cooled, it finally became transparent, and that first burst of light began its epic journey across space. The cosmic microwave background is a baby picture of the cosmos, a snapshot from its earliest childhood. For decades, this picture seemed perfectly smooth and uniform, but then our tools improved. We discovered that this uniform background is not perfectly smooth. It contains tiny temperature fluctuations, minuscule variations hotter and colder than the average by mere millionths of a degree. These tiny ripples are the most important seeds in cosmic history. They represent slight overdensities, regions where gravity had just a little more to pull on. Over billions of years, these minute imperfections grew, pulling in more and more matter, eventually giving rise to the vast cosmic web of galaxies, clusters, and superclusters we observe today. Every structure you see in the night sky, from the smallest dwarf galaxy to the largest filament of dark matter, originated from these quantum ripples imprinted on the cosmic microwave background. As one astronomer put it, the CMB is our most direct window into the early universe, a time capsule that has been delivering its message for over 13 billion years. Space missions like the Planck satellite have mapped these temperature fluctuations with breathtaking precision. These maps are like cosmic blueprints, revealing the universe's fundamental composition and confirming its age with incredible accuracy. Yet, this incredible precision has also revealed something unsettling. The maps contain strange anomalies, features that do not quite fit the predictions of our standard model. There are large patches of the sky that are slightly colder or warmer than they should be, and a mysterious alignment some call the axis of evil. These are not errors, they are real features of our cosmos that current physics struggles to explain. The universe's most pristine baby picture, it seems, holds clues to mysteries we are only beginning to grasp. The universe's baby picture holds a secret, a subtle crack in the cosmic mirror. When scientists created their most detailed maps of the cosmic microwave background, they expected a universe that looked the same in every direction, a fundamental principle known as isotropy. Instead, they found strange, large-scale features that break this rule. One of the most puzzling is a vast, unexplained cold spot, a region of space significantly chillier than the surrounding cosmic background. It is too large and too cold to be easily explained by the random fluctuations that seeded galaxies. Then there is the so-called axis of evil, a mysterious alignment where the hotter and colder patches in the cosmic microwave background appear to line up along a particular direction in space, almost as if the universe has a preferred axis. This is deeply unsettling because our standard model of cosmology insists there should be no special direction, no center, and no grand architectural plan. It would be like drawing dots randomly on a balloon, only to find they all form a perfect arrow when the balloon is inflated. Some researchers argue these are merely statistical flukes, the cosmic equivalent of seeing faces in clouds. Yet the anomalies persist through increasingly precise measurements. If they are real, their implications are staggering. One radical possibility is that these patterns are bruises, imprints from a colossal collision with another universe in a vast multiverse. The cold spot could be the shadow of a pre-Big Bang structure, a relic from a time before time, whose ghostly echo still lingers on the sky. Other theorists suggest our universe is not infinite, but has a complex, finite shape that twists the light from its infancy into these strange alignments. The debate is fierce, with experts divided on whether we are seeing the limits of our current models or the first faint hints of an entirely new cosmic reality. Major studies using powerful telescopes like the Planck satellite and future observatories are now focused on re-examining these irregularities, searching for the subtle fingerprints of new physics. These cosmic imperfections force us to ask a profound question. Is our universe truly the smooth, uniform expanse we thought it was, or does its origin story contain chapters we have not yet begun to read? These strange cosmic alignments are not the only puzzle hidden in the afterglow. An even more fundamental mystery lies in its profound uniformity. Why does the universe look the same in all directions? The cosmic microwave background radiation is almost perfectly smooth, with a nearly identical temperature in every patch of the sky. Yet, according to the standard Big Bang model, this should be impossible. Consider two distant regions on opposite sides of the observable universe. The light from these regions is only now reaching us, meaning they have been flying apart for nearly 14 billion years. In all that time, they have never been in contact. They are like two ships that set sail from the same port in opposite directions, losing sight of each other instantly. How could they possibly have agreed to be the exact same temperature, down to a tiny fraction of a degree? For them to reach thermal equilibrium, heat or information would have had to travel between them faster than the speed of light, which is a cosmic speed limit that nothing can break. This is the horizon problem, a deep flaw in the classic Big Bang story. It suggests that the universe we see was somehow connected and homogenized before the expansion we observe began. The most compelling solution proposed is cosmic inflation. Developed by physicists like Alan Guth, inflation suggests that a tiny, uniform patch of the primordial universe underwent a breathtakingly rapid expansion. In the first fraction of a second, the universe ballooned from smaller than a proton to a size larger than our entire observable cosmos. This exponential stretching would have ironed out any initial wrinkles, smoothing the universe to the incredible uniformity we detect. It is like taking a small, warm marble and inflating it to the size of the Earth, the temperature becoming nearly identical across its entire vast surface. Alan Guth famously called inflation the ultimate free lunch, a mechanism that could create a vast, flat, and uniform universe from almost nothing. While inflation is the leading idea, it is not the only one. Some theorists have proposed that the speed of light itself was not always constant. In the early universe, light may have traveled infinitely fast, allowing distant regions to communicate and equalize their temperatures instantly before settling into the constant speed we measure today. These competing ideas show how the horizon problem pushes our understanding to the very edge. It forces us to confront what happened in the first fleeting moments when the laws of physics as we know them were being forged. But if inflation solved the problem of uniformity, it created another, even more spectacular consequence. What did this process of explosive stretching leave behind in the fabric of space itself? That rapid stretching did more than just solve the uniformity problem. It left a permanent mark on the cosmos. Cosmic inflation proposes that in the first sliver of a second, the universe expanded faster than the speed of light itself. This was not matter moving through space, but space itself stretching at an exponential rate, taking a quantum speck and inflating it to a size larger than our entire observable universe in a time too short to comprehend. This explosive growth ironed out the cosmos, explaining its large-scale smoothness and its overall flat geometry, just as blowing up a balloon makes its surface appear flatter and flatter. The tiny quantum ripples that existed in that primordial speck were also stretched to astronomical sizes, eventually becoming the gravitational seeds for all future cosmic structure. the very same ripples we see imprinted in the cosmic microwave background. The specific pattern of these temperature variations, mapped with such precision by satellites, is considered a key piece of evidence for this incredible theory. Yet for all its explanatory power, inflation raises profound questions of its own. What was the engine that drove this phenomenal expansion, and what suddenly made it shut off? Physicists propose a hypothetical energy field called the Inflaton field, which is thought to have permeated the infant universe. Think of it like a strange, cosmic fuel that caused space to repel itself, driving the ultra-fast expansion. As this field decayed and lost its energy, that repulsive force vanished, and the universe transitioned into the more sedate, hot Big Bang expansion we are familiar with. The problem is, we have no direct proof this Inflaton field ever existed. It remains a compelling but elusive idea, a ghost in the cosmic machine. This leads to a fierce debate among cosmologists. Is inflation a testable scientific theory, or is it so flexible that it can explain almost any outcome? Some critics argue that if a theory can accommodate too many possibilities, it becomes difficult to disprove. Furthermore, many models of inflation naturally lead to a staggering consequence, an eternal multiverse. In this view, our entire cosmos is just one bubble in a vast, frothing sea of universes, each with its own unique properties and physical laws, endlessly spawning from the inflationary background. How could we ever test such a concept? The theory that so elegantly solved the horizon problem may have opened a door to an even grander and perhaps untestable reality. Inflation reshaped our narrative of the beginning, but it also pushed the ultimate origin story into a realm of speculation, leaving us to wonder what truly ignited the cosmic engine. The cosmic scaffolding for all this structure was built by an invisible hand. When astronomers like Vera Rubin first measured how fast stars orbit the centers of galaxies, they found something deeply perplexing. The outer stars were moving far too quickly. According to the laws of gravity and the amount of visible matter, these distant stars should have been flung off into the void, like a child spun too fast on a merry-go-round. The fact that they were not could only mean one thing. Galaxies are embedded within vast, massive halos of something we cannot see, a substance that does not emit, absorb, or reflect light. We call this mystery dark matter. Its gravitational grip is the only thing holding fast-spinning galaxies together. Vera Rubin's work on galaxy rotation curves provided some of the strongest evidence, revealing that this unseen component dominates the mass of every galaxy. The effects of dark matter extend far beyond single galaxies. Look at giant clusters of galaxies, and you will see them wrapped in faint, ghostly halos so massive they warp the fabric of space around them. This phenomenon, called gravitational lensing, acts like a cosmic magnifying glass. The immense gravity of a cluster bends the light from even more distant galaxies, distorting their images into faint arcs and rings. By mapping this distortion, astronomers can literally trace the outline of the invisible dark matter that causes it. Without this hidden mass, the universe would look utterly different. In sophisticated computer simulations of cosmic evolution, only when scientists include a generous helping of dark matter do the virtual universes produce the intricate web of filaments and clusters we observe in our own. Dark matter acted as the essential gravitational anchor, pulling ordinary matter together to form the first galaxies and stars. It is the cosmic skeleton upon which the visible universe is built. So what is this mysterious substance? The leading candidates are known as WIMP, or weakly interacting massive particles. These are hypothetical particles that are heavy, and as their name suggests, interact with ordinary matter only through gravity and the weak nuclear force, making them incredibly difficult to catch. For decades, physicists have been running exquisitely sensitive experiments deep underground, in old mines and tunnels, shielded from cosmic rays. They wait patiently for the once-in-a-lifetime tremor that might signal a dark matter particle bumping into an atomic nucleus. Yet so far, the detectors have remained silent. Other ideas propose different candidates like actions, which are incredibly light particles, or even primordial black holes formed in the universe's first instance. The puzzle only deepens when you consider the evidence. We can map dark matter's gravitational shadow across the cosmos. We know it is 5 times more abundant than all the normal matter we are made of, and we see its undeniable influence on the largest scales. So if it is everywhere, passing through our bodies and our planet every second, why does it remain so stubbornly invisible? This question strikes at the heart of modern physics. Is our understanding of gravity itself incomplete on cosmic scales, or are we on the verge of detecting a particle that will redefine the fundamental ingredients of reality? This invisible enigma holds the blueprint for our cosmic home, yet its true nature is a secret the universe has so far refused to surrender. The mystery deepens with a force even more alien than dark matter. While dark matter pulls the cosmos together with its relentless gravity, something else is actively pushing it apart. This is the enigma of dark energy, a repulsive force that seems to be woven into the very fabric of space itself. Its discovery was one of the most shocking revelations in modern cosmology. In the late 1990s, 2 independent teams of astronomers were studying distant stellar explosions, known as Type 1, a supernova. These supernovae act as cosmic lighthouses, their standard brightness allowing scientists to gauge their distance with incredible precision. By measuring how much the light from these explosions was stretched by the universe's expansion, the teams made a startling realization. The most distant supernovae were fainter than they should have been, meaning they were farther away than anyone had predicted. The universe's expansion was not slowing down, as everyone had assumed under gravity's pull. It was speeding up. This discovery of an accelerating cosmos was so profound it earned the researchers the Nobel Prize in Physics. A mysterious energy, a kind of cosmic anti-gravity, was overwhelming the collective gravitational attraction of all the matter in the universe. This force is what we now call dark energy. The leading explanation for it is a concept Einstein once proposed and then discarded, the cosmological constant. This represents a constant energy density inherent to empty space itself. Think of the vacuum of space not as truly empty, but as a seething foam of virtual particles constantly flickering in and out of existence. This quantum jitter is thought to generate a repulsive pressure, causing space itself to expand at an ever-increasing rate. It is like an invisible engine, constantly adding new space between galaxies. The implications for the universe's ultimate fate are chilling. If dark energy continues to dominate, as all evidence suggests it will, the cosmic expansion will accelerate forever. Over trillions of years, galaxies outside our local group will be pushed away so far and so fast that their light will never reach us. The observable universe will shrink to a relative island of stars, set against an endless, expanding blackness. This scenario is often called the Big Freeze, a cold, dark, and empty end. Yet, dark energy presents a colossal puzzle for physicists. When they calculate how strong this vacuum energy should be based on quantum theory, the number is absurdly large, a value with 120 zeros more than what we actually observe. It is the worst prediction in the history of physics. Why is the measured value of dark energy so incredibly small, yet just right to have become noticeable only now in cosmic history? This fine-tuning problem suggests we are missing something fundamental. Is dark energy truly constant, or could it be a dynamic field that changes over time? Major projects like the Dark Energy Survey are meticulously mapping millions of galaxies to measure the expansion history of the universe with unprecedented detail, hoping to uncover the true nature of this force. The mystery of dark energy strikes at the core of our understanding, forcing us to ask why the void of space has this faint, repulsive energy, and what its existence means for the ultimate destiny of everything. To understand the universe's true origin, we must journey back before its first tick. Before even a single second had passed, we reach a boundary known as Planck time, a moment so early it defies our imagination. This is the 10 to the power of negative 43 seconds mark, a decimal point followed by 42 zeros and then a 1. At this threshold, our knowledge of physics simply stops working. The universe was compressed into a volume so small and was so unimaginably hot that the very ideas of space and time lose their meaning. We are looking at a realm of pure energy where the gravitational force was as strong as the other fundamental forces and the cosmos was a seething, chaotic foam. This is the domain of quantum gravity, a theory that remains the holy grail of modern physics. Without it, the story of the Big Bang is incomplete. We can describe the universe from a fraction of a second after its birth with stunning accuracy, but the moment of creation itself is a blur. The challenge is the fundamental conflict between our two most successful theories. Einstein's general relativity beautifully describes the cosmos on the largest scales, the warping of space and time by mass and energy. Quantum mechanics with equal brilliance governs the bizarre, probabilistic world of the atom. But in the furnace of the Big Bang's first instant, where the entire universe was smaller than a single subatomic particle, these two theories collide and break down. General relativity predicts a singularity, a point of infinite density where its own equations fail. Quantum mechanics, however, abhors such infinities. To peer into this first moment, we need a theory that can marry the two. This is where ideas like string theory and loop quantum gravity enter the stage, offering potential paths forward, yet they remain unproven mathematical landscapes. String theory suggests that the fundamental constituents of reality are not point particles, but tiny, vibrating strings. Their different resonant frequencies would give rise to all the particles and forces we see. In this view, the Big Bang could have been a collision between higher dimensional membranes, or perhaps a phase transition where these strings condensed from a more symmetric state. Loop quantum gravity takes a different approach, proposing that space itself is not smooth and continuous, but woven from a fabric of tiny, finite loops. Think of the fabric of spacetime as a tapestry made of individual threads. At the Planck scale, this tapestry becomes a dynamic, ever-changing network. This theory leads to a startling possibility that the Big Bang was not a true beginning, but a big bounce from a previous universe that had collapsed. Both theories try to describe the nature of the quantum foam, a concept for the turbulent structure of spacetime at this tiny scale. In this foam, wormholes might constantly blink in and out of existence, and virtual particles spawn from nothingness. It is a realm of constant, violent fluctuation where the concepts of here and there, before and after, cease to have any stable definition. As one physicist lamented, the problem with quantum gravity is not that our experiments give the wrong answers, but that we cannot perform the experiments at all. The energies required to test these ideas are a quintillion times beyond what our most powerful particle colliders can achieve. This leaves us at a profound philosophical crossroads. Did time truly have a beginning, a first moment that we can point to? Or was there a pre-existing state, a cyclic universe or a multiverse, from which our own cosmos was born? We are forced to confront the limits of our own language and logic, to ask what reality was like when reality itself had not yet settled into the familiar rules we know. The cosmic dawn remains the ultimate frontier, a brief, unknowable moment from which everything we see and are ultimately emerged. The universe's very existence hinges on a single, unexplained preference. We are surrounded by matter, from the planets and stars to the air we breathe, yet our best theories tell us this should not be the case. In the first moments of the hot Big Bang, energy should have condensed into equal amounts of matter and antimatter. For every particle of matter created, a mirror image particle of antimatter should have been born alongside it. The problem is, when matter and antimatter meet, they annihilate in a flash of pure energy. If the universe had begun in perfect balance, all of its particles should have mutually destroyed one another, leaving behind a sea of radiation and nothing more. The fact that we are here means that this perfect symmetry was broken. Somewhere, somehow, a tiny excess of matter was left over after the Great Annihilation, about one extra particle of matter for every billion matter-antimatter pairs. This is the Baryogenesis problem, and it asks why the cosmos is made of something rather than almost nothing. The quest to solve it takes us into the heart of particle physics. In the 1960s, Russian physicist Andrei Sakharov outlined 3 essential conditions needed to create a matter-dominated universe. The first is a process that violates baryon number, meaning it can change the total amount of matter in the universe. The second is a violation of both charge and parity symmetry, known as CP violation. This is a subtle but crucial idea. It means that certain physical processes should behave differently if you replace particles with their antiparticles and also view them in a mirror. Imagine a clock that, when reversed and viewed in a mirror, runs at a slightly different speed. That is the kind of broken symmetry physicists are searching for. The third Sakharov condition is that all this must have happened out of thermal equilibrium, a departure from the smooth, hot soup of the early universe. We have actually observed CP violation in experiments with exotic particles called kaons and B mesons. The effect is incredibly small, but it proves the laws of physics do, in fact, have a tiny built-in preference for matter over antimatter. The problem is, the amount of CP violation we have measured is not nearly enough to account for the overwhelming dominance of matter we see in the cosmos today. So where did the rest of the asymmetry come from? This is where theorists propose grander ideas. Some point to the mysteries of the neutrino. These ghostly particles barely interact with matter, but if they are their own antiparticles and have certain properties, their interactions in the early universe could have tipped the scales decisively in favor of matter. Others look to grand unified theories, which propose that 3 of the fundamental forces were once a single, unified force. The splitting of this force in the universe's first moments could have produced the necessary processes to generate more matter. To test these ideas, scientists use colossal machines like the Large Hadron Collider. By smashing particles together at nearly the speed of light, they recreate the extreme conditions of the primordial universe, watching intently for any rare decay or interaction that shows a clear preference for matter. Every galaxy and every star is a monument to that ancient, 1 in a billion imbalance. The entire visible universe is the leftover ash from a near-total annihilation, a cosmic victory for matter so slight it defies measurement, yet so consequential it made our world possible. These faint ripples in space-time are the universe's first tremors. Primordial gravitational waves are not vibrations of matter or light, but oscillations in the very fabric of reality, generated during the universe's most violent birth pangs. According to the theory of cosmic inflation, the same explosive expansion that smoothed the cosmos should have sent powerful shock waves through space-time itself. Think of the infant universe as a pond of pure space and time, and the process of inflation as a colossal stone thrown into its center, the impact would send powerful, expanding ripples across the entire pond, warping everything in their path. These are the primordial gravitational waves, a fossil imprint left by the inflationary engine. They carry information from a time far earlier than the cosmic microwave background, from the first sliver of a second when the universe was a seething quantum foam. To detect these ancient whispers, scientists look for a unique signature imprinted on the oldest light we can see. As the gravitational waves from inflation traveled through the primordial plasma, they would have subtly twisted the polarization of the cosmic microwave background radiation. This creates a specific swirling pattern known as B-mode polarization, a faint, curly signature frozen in the sky. Finding this pattern is the holy grail for cosmologists, as it would be direct, smoking gun evidence for inflation. The hunt for this signal reached a fever pitch with the BICEP 2 experiment, a powerful telescope stationed at the South Pole. In 2014, the team announced a monumental discovery. They had found the telltale B-mode patterns in their data. The scientific world erupted with excitement. It seemed we had our first glimpse into the universe's first instance, but the celebration was short-lived. Further analysis, crucially incorporating data from the Planck satellite, revealed a devastating complication. The signal BICEP 2 had detected could be entirely explained by interstellar dust within our own Milky Way galaxy. This cosmic dust, when magnetically aligned, can produce a swirling polarization pattern that mimics the inflationary signal perfectly. The announcement turned from a triumph into a cautionary tale about the immense challenges of this search. The debate that followed was fierce, highlighting the razor's edge on which this field operates. Experts emphasized that a true, confirmed detection would be one of the most profound discoveries in the history of science. It would not only prove that inflation happened, but would also tell us the energy scale at which it occurred, effectively revealing what powered the cosmic engine. The strength of the gravitational wave signal is directly tied to the intensity of the inflationary expansion. Detecting a strong signal would point to a violent, high-energy event, while a weaker one or a non-detection might steer us toward gentler models. This relentless pursuit drives a new generation of ambitious experiments, with ever more sensitive telescopes and sophisticated methods to filter out the dusty foreground. They are listening for the faintest echo of creation, a tremor in space-time that has been traveling for over 13 billion years. The search for these primordial ripples is a journey to the ultimate horizon of our knowledge, a direct line back to the moment everything began. This idea of an eternal, self-replicating cosmos leads to one of the most staggering possibilities in all of science. Our entire universe, with its hundreds of billions of galaxies, might be just one tiny bubble in a vast, frothing cosmic ocean. This is the Multiverse Hypothesis, the suggestion that we are part of a vast ensemble of universes, each with its own unique reality. The mechanism for this is often tied directly to the theory of inflation. If that repulsive Inflaton field did not completely decay everywhere at once, it could continue driving exponential expansion in other regions, eternally spawning new universe bubbles. Picture a pot of water beginning to boil. Each rising steam bubble is a separate universe, nucleating within the ever-expanding background of the inflationary energy. Our Big Bang was simply the moment our particular bubble formed and began its own internal evolution. String theory adds another layer to this dizzying picture. It suggests the number of possible stable configurations for the extra dimensions it proposes is astronomically large, perhaps 10 to the power of 500. Each configuration would correspond to a universe with a different set of physical laws and constants. In this string theory landscape, every possible universe is real, existing somewhere in the multiverse. This provides a potential answer to one of the deepest puzzles, the fine-tuning problem. Why do the fundamental constants of nature, like the strength of gravity or the mass of an electron, seem perfectly calibrated to allow for the existence of stars, planets, and life? If there are countless universes, each with random physical laws, then it is no surprise we find ourselves in one of the rare, bio-friendly ones. This line of reasoning is known as the Anthropic Principle. As physicist Max Tegmark has proposed, this could mean that all mathematical structures that can exist do exist in some physical reality. Our universe is not special, it is just typical among the subset that can support conscious observers. Yet, this idea is met with fierce criticism. Prominent scientists argue that if a theory predicts everything, it effectively predicts nothing. They contend that a multiverse is fundamentally untestable, as we could never observe or interact with these other cosmic domains. It risks moving cosmology from a science based on evidence into the realm of pure philosophy. If the multiverse is real, then the Big Bang was not a unique beginning of everything, but merely a local event in a much grander, perhaps infinite, meta-universe. Our cosmic story, for all its grandeur, becomes a single chapter in an endless library of realities. This forces us to confront a humbling question. Does the multiverse represent the ultimate triumph of scientific imagination, or is it a sign that we have reached the very limits of what is knowable? General relativity paints a picture of an ultimate beginning, a singularity where all of space, time, and matter were crushed into an infinitely dense point. Yet this very prediction is a sign that the theory has reached its breaking point. Infinite density is not a physical answer, it is a mathematical cry for help, a signal that we need a deeper theory of reality. So did the universe truly have a starting pistol, a first moment when time itself flickered into being, or is that just an illusion created by our incomplete knowledge? Compelling alternatives suggest our cosmos has no true beginning or end, only an eternal cycle of transformation. In the framework of loop quantum cosmology, for instance, the Big Bang could have been a big bounce. Imagine the previous cosmic era not vanishing into nothingness, but contracting under its own gravity until it reached a point of immense, but not infinite, density. The repulsive force generated by the quantum nature of spacetime itself would then have caused a cosmic rebound, a great bounce that launched the expansion we see today. Our universe, in this view, could be the latest incarnation in an endless series of cosmic breaths, expanding and contracting through eternity. Other models propose a cyclic universe, where colliding multidimensional membranes in a higher dimensional space trigger repeated big bangs, a perpetual cosmic reset. The great physicist Stephen Hawking approached the question of a beginning from another angle, suggesting that asking what came before the Big Bang is like asking what is north of the North Pole. He proposed a no-boundary condition where time becomes like another dimension of space when traced back to the origin, meaning the universe would be entirely self-contained, with no singular boundary or edge to mark a start. This elegantly sidesteps the need for a first cause, but it leaves us grappling with a profound abstraction. If we could rewind the cosmic film, would we see the screen go blank, or would we find the film is a loop with no start and no finish? The debate is far from settled. Some cosmologists insist that time, as we understand it, absolutely began at the Big Bang. Others argue just as forcefully that a pre-Big Bang era must have existed, a phase of cosmic history forever lost to us. This fundamental question pushes past astronomy and into the realm of philosophy. It asks us to consider the very nature of existence and whether the concept of a true beginning is anything more than a comforting story we tell ourselves. The echo of that first explosion may not be the sound of a starting gun, but simply the turning of a page in an infinite book. The largest structures in the cosmos were born from the smallest possible events. Within the first sliver of a second, the universe was a turbulent sea of quantum foam, where empty space was not truly empty. It fizzled with energy, with pairs of virtual particles and antiparticles constantly blinking into existence and annihilating each other an instant later. This is the realm of quantum uncertainty, where temporary fluctuations in energy are not just allowed, they are required. In that primordial fireball, these fleeting quantum ripples were the only structures that existed. Then came inflation. That brief period of hyper-expansion acted like a cosmic magnifying glass, stretching these subatomic wrinkles to astronomical proportions. A random flicker that was once smaller than a proton was suddenly inflated to a scale of light years, frozen into the fabric of space-time as a minute variation in density. These imprints are the quantum seeds for everything we see today. We can actually see these seeds in the cosmic microwave background. The tiny temperature differences, those hot and cold spots, are the direct descendants of those initial quantum fluctuations. They are the blueprint showing us where matter was ever so slightly more or less dense when the universe was only 380,000 years old. After this light was set free, gravity began its slow, relentless work. For hundreds of millions of years, it pulled on those slightly denser regions. The dark matter already in place formed a deep gravitational well, a cosmic scaffold. Ordinary matter, primarily hydrogen and helium gas, was then drawn into these dark matter halos. As the gas collected, it condensed, heated up, and eventually ignited, forming the first stars and the earliest galaxies. These infant galaxies then continued to merge and cluster, drawn together by the underlying gravitational template laid down by those ancient quantum seeds. This entire process, from quantum jitter to glittering galaxy, is confirmed by our most powerful supercomputer simulations. Scientists program the initial conditions using the precise patterns observed in the cosmic microwave background. They add the known ingredients of the universe, including a generous portion of dark matter. When they press play, the simulation runs the clock forward for over 13 billion years. The result is astonishing. The virtual universe evolves to form a cosmic web of filaments and voids, with galaxies clustering in patterns that are indistinguishable from what our telescopes actually observe. It is a profound validation that our understanding of this chain of events, while incomplete, is fundamentally correct. The universe we inhabit is a magnified version of its quantum past. This connection forces a staggering question. Does the entire cosmic architecture, from the grandest supercluster to our own Milky Way, ultimately stem from random quantum chance? Are we, and everything we see, the result of a cosmic lottery drawn in the first fleeting moments? The bridge between the quantum world and the cosmos at large is now one of the strongest pillars of modern cosmology. It reveals a universe where the rules governing the smallest particles are directly responsible for the largest structures, a beautiful and humbling link between the micro and the macro. If these tiny fluctuations had been just a little different, the cosmos would be a vastly emptier or perhaps more crowded place. These faint quantum seeds were not the only relics forged in the early fire. Within the first few seconds of the universe, a second cosmic background was created, one made not of light, but of ghostly particles called neutrinos. Billions of these nearly massless entities flood through your body every second, completely unnoticed, a silent rain from the cosmos. They are so reluctant to interact with normal matter that most pass straight through our entire planet as if it were empty space. This aloof nature is precisely why they were among the first particles to break free from the primordial plasma. Just 1 second after the Big Bang, the expanding universe had cooled enough for neutrinos to decouple, to stop interacting with the hot soup of particles and light. They have been streaming freely through the cosmos ever since, forming a cosmic neutrino background. This is a fossil even more ancient than the cosmic microwave background, a snapshot from the universe's very first second of existence. Detecting this relic sea of neutrinos is one of the monumental challenges of modern physics. These particles carry so little energy now, after 13.8 billion years of cosmic expansion, that they are effectively frozen, moving at speeds far less than their original near-light velocity. Catching one is like trying to hear a single whisper in a hurricane. As one particle physicist noted, we are essentially blind to the lowest energy neutrinos, the very ones that would constitute this primordial background. Our current detectors are tuned for the high-energy neutrinos blasted out by stellar explosions, not these faint, cold ghosts from the beginning. Yet we know they must be there, and their early influence is written into the cosmos. During the first few minutes, an epoch known as Big Bang Nucleosynthesis, the presence of these high-speed neutrinos played a crucial role in determining the ultimate recipe of the universe. Their relentless motion helped govern the nuclear reactions that forged the first atomic nuclei, primarily hydrogen and helium. The observed abundance of these light elements matches our predictions perfectly only when we account for the number of neutrino species, a powerful confirmation of their early presence. Later, as the cosmic structures began to form, these relic neutrinos continued to shape events. Because they were moving so fast, they could not be trapped by the weak gravitational pull of the early density fluctuations. They streamed out of small, nascent clumps of matter, effectively smoothing out the smallest scales of the cosmic web. This neutrino wash suppressed the formation of the very smallest dwarf galaxies, leaving a subtle imprint on the distribution of matter we can still infer today. The greatest mystery they present is their mass. The standard model of particle physics long assumed neutrinos were completely massless, but experiments have definitively proven they have a tiny, non-zero mass. We do not know what the actual mass is, only that it is vanishingly small. This single unknown could be the key to physics beyond the standard model. Their tiny mass might also hold the answer to another great puzzle, the Matter-Antimatter Asymmetry. If neutrinos are their own antiparticles, a special class known as Majorana particles, their rare decays in the early universe could have been the mechanism that favored matter, creating the 1 in a billion surplus that makes up our world. Hunting for these effects drives ambitious next-generation experiments. Projects like Ptolemy aim to capture relic neutrinos by spotting the unimaginably faint signal when one interacts with a radioactive atom. Success would give us a direct window into the first second of time, a data stream from the moment the neutrino background decoupled. These elusive particles are not just cosmic spectators, they are active architects of our reality. Their ghostly passage through the cosmos carries secrets about the universe's fundamental laws and its very first moments, a hidden chapter of creation waiting to be read. The universe's first recipe holds a single, stubborn error. In the initial minutes after the Big Bang, during the epoch known as nucleosynthesis, the cosmos was a nuclear fusion reactor, forging the lightest elements from a primordial soup of protons and neutrons. The calculations are exquisitely precise, predicting how much hydrogen, helium, and a trace amount of lithium should have been created. For hydrogen and helium, the predictions match the amounts observed in the oldest stars and primordial gas clouds almost perfectly. But for lithium, the numbers fail. The oldest stars in our galaxy contain only about 1/3 of the lithium that our models of the Big Bang say they should. This is the lithium problem, a small but persistent crack in our otherwise robust story of the universe's first moments. Astrophysicists have studied the atmospheres of these ancient, metal-poor stars for decades, using their light like a chemical fingerprint to measure elemental abundances. The result is always the same: the lithium level is consistently and mysteriously low. This is not a small observational error. It is a glaring discrepancy that forces us to question our understanding of those first few minutes. Could our measurements of the nuclear reaction rates involved be slightly off? Perhaps a rare, unknown nuclear reaction in the early universe destroyed lithium as fast as it formed. Or maybe the solution lies not in nuclear physics, but in the stars themselves. Some theorists propose that these ancient stars have internal processes that slowly drag lithium from their surfaces down into their hotter interiors, where it is destroyed, effectively hiding the original amount. Other explanations are more radical. The lithium shortfall could be a sign of new physics at play in the early cosmos. What if an unknown, exotic particle was present during nucleosynthesis, interacting with the primordial plasma and altering the delicate nuclear chain reactions that built the lithium nuclei? This hypothetical particle could have decayed, releasing energy that changed the reaction rates just enough to suppress lithium production. The discrepancy is a tantalizing clue, a potential footprint of something beyond our standard model of particle physics, frozen in the atmospheres of the most ancient stars we can find. This small problem carries a profound message. It reminds us that even the most well-tested pillars of cosmology can harbor deep mysteries. The lithium problem is a quiet but persistent voice suggesting that our map of the universe's first few minutes is not yet complete. What other secrets are hidden within the faint chemical signatures of the first stars? The search for an answer continues to drive new observations and more sophisticated models, a testament to the fact that the story of creation is still being written, one lithium atom at a time. The universe's final act is written in its first moments. Every galaxy racing away from us today is following a trajectory set by the initial force of that primordial explosion, a path now guided by the mysterious push of dark energy. This relentless expansion points toward a dominant and deeply chilling destiny known as the heat death. In this scenario, dark energy continues its work unchallenged. Galaxies will be pushed beyond our cosmic horizon, their light fading from view forever. Stars will exhaust their nuclear fuel and wink out one by one. Eventually, even the black holes will evaporate, leaving behind a universe that is cold, utterly dark, and almost perfectly empty. It is a quiet, gradual fade to black, a state of maximum entropy where no energy can flow and no new story can ever be told. As one cosmologist solemnly noted, it would be the ultimate triumph of silence over substance. But is this frozen end the only possibility? Another classic scenario is the Big Crunch, a dramatic reversal of our current expansion. For this to happen, the density of matter in the universe would need to be high enough for gravity to eventually overcome dark energy's repulsive force. The cosmos would slow its flight, stop, and then begin a catastrophic collapse. Galaxies would rush together, the background temperature of space would soar, and all of creation would be compressed back toward an infinitely hot, dense state, a mirror of the Big Bang, perhaps even giving rise to a new universe in a cyclical rebirth. Yet our measurements of the cosmos's shape and the accelerating expansion strongly suggest there is simply not enough matter for gravity to win this cosmic tug of war. The data points away from a fiery collapse and toward a cold, drawn-out end. An even more violent alternative is the Big Rip. This fate arises if the strength of dark energy increases over time. In this scenario, dark energy would not just push galaxies apart, its repulsive force would grow so powerful that it would overwhelm all the forces that hold things together. First, galaxy clusters would be torn asunder, then individual galaxies would be shredded. In the final moments, stars and planets would be ripped apart, and finally, atoms and even subatomic particles would be torn to pieces. The very fabric of spacetime would be shredded in a final, catastrophic instant. While current data does not strongly support this model, it remains a haunting reminder of dark energy's potential power. These are not just abstract ideas, they are the logical endpoints of the equations we use to describe our universe, a direct consequence of the balance between the initial explosive force and the contents of the cosmos. The trajectory was set in the first fractions of a second, and we are now simply riding the curve. The silence that will one day descend is the long echo of that first tremendous explosion, a story that began in fire and appears destined to end in ice. Our ability to peer back in time hinges on a silent revolution in our cosmic vision. The Hubble Space Telescope, orbiting far above the distorting veil of our atmosphere, gave us our first deep look into the universe's childhood. Its iconic deep field images, created by staring at a seemingly empty patch of sky for days, revealed a universe teeming with thousands of faint, infant galaxies, each a smudge of light from a time when the cosmos was just taking shape. These were not the grand spirals we see today, but smaller, irregular building blocks, the very stuff from which our own galaxy would later form. Hubble showed us the universe in its awkward, formative years. But to see the first dawn of starlight, we needed to look even deeper into infrared wavelengths. The James Webb Space Telescope is that next-generation time machine. Its colossal golden mirror is designed to catch the faint, stretched light from the very first stars and galaxies, objects whose ultraviolet glow has been redshifted into the infrared by the universe's relentless expansion. James Webb is not just seeing farther, it is seeing differently, peering through cosmic dust to witness the birth of the first stellar nurseries and to analyze the atmospheres of distant exoplanets, searching for the chemical fingerprints of potential life. It is our most powerful window into the era of reionization, when the first brilliant stars burned away the primordial fog of hydrogen gas, forever clearing the cosmos for light to travel freely. The hunt does not stop with light. The Future Laser Interferometer Space Antenna, or LISA, will open an entirely new sense by detecting gravitational waves. While ground-based observatories have felt the tremors from merging black holes, LISA will operate in space, free from terrestrial vibrations, allowing it to sense the low-frequency ripples from the most colossal events. It could listen for the echoes of supermassive black hole mergers from the early universe, and most thrillingly, the primordial gravitational waves from inflation itself, a direct signal from a time before the first light. Meanwhile, the Euclid Space Telescope is meticulously mapping the dark universe. By observing billions of galaxies, it will trace the invisible scaffolding of dark matter through its gravitational lensing effects and measure the history of cosmic expansion with unprecedented precision, hoping to uncover the true nature of dark energy. Is it a constant force or does it change over time? The answer will dictate the ultimate fate of everything. Each of these instruments is a specialized tool for dissecting the cosmic past. As one project scientist for James Webb remarked, we are essentially building a time machine piece by piece. With every technological leap, we peel back another layer of time, moving from the cosmic toddler years glimpsed by Hubble to the infancy we hope to see with James Webb, and perhaps one day with even more advanced tools to the very moment of birth itself. What will these new eyes see when they stare into the deepest dark, and what old mysteries will they finally lay to rest? This fine-tuning of the cosmos is so precise it feels like a cosmic conspiracy. The strength of gravity, the mass of an electron, the force that binds atomic nuclei, every one of these fundamental constants appears perfectly calibrated. If any were slightly different, the universe would be sterile. A little stronger gravity and stars would burn out in millions of years, far too quickly for life to evolve. A slightly weaker nuclear force and hydrogen would never fuse into helium, leaving a universe with no stars at all. This staggering precision demands an explanation. Is it mere astronomical luck, or does it point toward something deeper? This is the fine-tuning problem, and the most discussed answer is known as the Anthropic Principle. In its simplest form, the weak Anthropic Principle states that we should not be surprised to find ourselves in a universe capable of supporting life. Of course, we observe conditions suitable for our existence because we are here to do the observing. It is a statement about selection bias, like a lottery winner marveling at their odds without considering the millions who did not win. The strong Anthropic Principle takes a more provocative stance. It suggests that the universe must, in some sense, have properties that allow life to develop at some stage in its history. This version edges toward the idea of a universe with a built-in preference for consciousness, a notion that resonates with both philosophical and theological perspectives. For many scientists, however, the most compelling resolution to fine-tuning lies in the multiverse. If an infinite or near-infinite number of universes exist, each with its own random set of physical laws and constants, then it becomes a statistical certainty that a few will, by pure chance, have the right recipe for life. We simply happen to live in one of those rare, bio-friendly bubbles. There is no grand design, only an immense cosmic lottery, and we hold the winning ticket. This idea sparks fierce debate. Proponents argue it is a natural extension of inflationary cosmology, a logical consequence of our best theories. Critics counter that the Anthropic Principle is a tautology, a fancy way of saying we exist because we exist. They argue it halts scientific inquiry, replacing the search for a fundamental reason for the constants with a shrug of cosmic chance. If every possible universe exists, then the theory can explain anything and thus predicts nothing. Philosophers weigh in, questioning whether this principle bridges science and meaning or simply highlights the limits of our knowledge. Does the fact that we are here to ponder the question tell us something profound about the cosmos? The Anthropic Principle, in all its forms, forces a humbling confrontation. It connects the vast, impersonal machinery of the cosmos to the intimate fact of our own awareness. We are not just passive observers of a random universe, but active products of its specific and seemingly improbable laws. This leaves us with a haunting reflection. Are the constants of nature a random fluke in an endless multiverse, or could our ability to measure and question them be part of a deeper, yet undiscovered cosmic story? The quest to understand the universe's first explosion leads us to a great divide in physics. On one side, Einstein's general relativity paints a cosmic landscape of warping space and time. On the other, quantum mechanics governs the frantic, probabilistic dance of the subatomic world. Each theory is brilliantly successful in its own domain, but they speak different languages and obey different rules. Where they meet, at the moment of the Big Bang itself, our mathematics breaks down into meaningless infinities. To cross this divide, physicists are hunting for a theory of everything, a single framework that can describe the cosmos from its largest scales down to its tiniest constituents. Two towering yet unproven ideas dominate this search. The first is string theory. It proposes a radical shift in what we consider fundamental. Imagine that the electrons, quarks, and photons making up our world are not zero-dimensional points, but incredibly tiny, vibrating loops of energy, smaller than a proton by a factor of a billion. Just as different vibrations of a violin string create distinct musical notes, the different resonant frequencies of these strings would give rise to all the diverse particles and forces we observe. One vibration pattern might be an electron, another a photon. The theory's elegance, however, comes with a formidable requirement: extra dimensions of space. For the math to work, strings must vibrate in not just the 3 spatial dimensions we experience, but in 10 or more. These extra dimensions would be curled up or compactified into shapes far too small for us to perceive directly. The promise of string theory is immense. It naturally includes gravity by describing the graviton, the hypothetical carrier of the gravitational force, as a particular string vibration. It aims to weave all forces and particles into a single, coherent tapestry. Yet, as leading theorist Edward Witten has reflected, string theory is a part of 21st century physics that fell into the 20th century by accident. We simply lack the tools to test its predictions. The energy required to probe these tiny scales is far beyond any particle collider we can build. This leads to another profound challenge: the string theory landscape. The number of possible ways for those extra dimensions to curl up is astronomical, perhaps 10 to the power of 500. Each configuration could correspond to a different universe with different physical laws. This dizzying plurality makes it difficult to derive unique, testable predictions for our own cosmos. In stark contrast, loop quantum gravity takes a different path. Instead of replacing particles with strings, it focuses on the fabric of spacetime itself. This theory proposes that space is not a smooth, continuous background, as Einstein described. Instead, it is woven from a network of finite, indivisible loops. Picture the fabric of your shirt. Up close, you see it is made of individual threads. Loop quantum gravity suggests spacetime is similar, a tapestry of tiny, interwoven threads of space. These loops form a dynamic, ever-changing structure often called spin foam. This quantum nature of space resolves the singularity at the Big Bang, replacing the point of infinite density with a quantum bounce. Our universe, in this view, could be the result of a great rebound from a previous cosmic era. The challenge here is equally daunting. While loop quantum gravity elegantly quantizes space, it has so far struggled to incorporate all the other forces of nature with the same seamless grace that string theory aims for. Both frameworks represent monumental intellectual achievements, yet they remain locked in a kind of stalemate, each brilliant in its own way but incomplete. They are the best maps we have for the terra incognita of the quantum gravity realm, the final frontier we must cross to truly hear the story the first explosion is trying to tell. We are cosmic archaeologists sifting through the rubble of time to reconstruct the story of everything. Our tools are not shovels and brushes, but telescopes and supercomputers, digging through layers of history encoded in light. Each observation is a fossil, a fragment of a past era we can piece together into a coherent narrative. Just as an archaeologist uses pottery shards to date a civilization, we use the light from distant galaxies to trace the evolution of the cosmos. The most fundamental tool in this kit is the measurement of redshift. When we observe a galaxy, its light is often stretched toward the red end of the spectrum, a direct result of the expansion of the universe stretching the wavelengths of light during its long journey to us. The greater the redshift, the farther away the galaxy, and the further back in time we are looking. By conducting massive redshift surveys, we can create three-dimensional maps of the universe, plotting the positions of millions of galaxies to reveal the grand architecture of the cosmic web. These maps show the vast filaments of dark matter and galaxies woven around immense, empty voids, a structure that mirrors the tiny seeds seen in the cosmic microwave background. Projects like the Sloan Digital Sky Survey have been pioneers in this field, using a specialized telescope to automatically scan the sky night after night, cataloging the spectra of countless celestial objects. This painstaking work has given us our first detailed charts of the cosmic continent, revealing the true scale of the universe's large-scale structure. The data these projects generate is almost unimaginably vast. Data scientists working in cosmology speak in terms of petabytes, a volume of information that would take thousands of years to watch on video. They develop sophisticated algorithms to sift through this digital universe, searching for subtle patterns that reveal the influence of dark energy or the subtle distortions of gravitational lensing. It is a detective story written in code and starlight. At the very foundation of this entire reconstruction lies the ultimate time capsule, the cosmic microwave background. This fossil radiation is our deepest core sample, drilled all the way back to the universe's infancy. Its temperature fluctuations are the primordial imprints, the initial conditions from which all later structure grew. By comparing the patterns in this ancient light with the galaxy maps we see today, we can test our models of cosmic evolution with incredible precision. We can run the film of the universe backwards in simulations, starting with those quantum ripples and watching as gravity sculpts them into a virtual cosmos that should match our own. When the simulation produces a universe that looks like the one we inhabit, we know we are on the right track. This entire process raises a thrilling question. As our data becomes ever more precise, what will it reveal about the very first instance? Could we one day find, hidden within the statistics of galaxy distributions or the polarization of the CMB, a subtle signature of what preceded the Big Bang itself? Every new data point is another piece of the puzzle, helping us refine the story of that first tremendous explosion and its enduring echoes. The sheer scale of cosmic history forces a humbling perspective on our own existence. Every element in our bodies was forged in the hearts of long-dead stars, and our planet is a fleeting speck in a universe that has been expanding for nearly 14 billion years. This scientific narrative of the Big Bang, a universe with a definite beginning, collides with some of humanity's oldest philosophical and religious questions. If the universe had a starting point, what or who set it in motion? This line of inquiry is known as the cosmological argument, suggesting that the chain of cause and effect we see in the world must ultimately lead back to a first cause, an uncaused cause that began the entire sequence. For many theologians throughout history, this first cause has been synonymous with a divine creator, a being outside of time and space who initiated the cosmos. The Big Bang theory, with its definitive starting point, seemed to some to provide a scientific moment of creation that aligned with this ancient idea. Yet science itself remains silent on the question of a creator, dealing in observable mechanisms rather than ultimate purpose. The theory describes how the universe evolved from a hot, dense state, but it cannot answer why there is something rather than nothing. This pushes us into the realm of metaphysics, where science and philosophy meet. What is the nature of time before the Big Bang? Our current physics suggests that time itself began with the expansion of the universe. Asking what came before the Big Bang, then, might be as meaningless as asking what is north of the North Pole. There is no before in the way we understand it, because time did not exist. This concept is incredibly difficult to grasp, as our minds are wired to think in terms of cause and effect unfolding within a timeline. If there was no time before the Big Bang, then the universe may not have been caused by anything at all. It could simply be a brute fact of existence, a spontaneous quantum fluctuation in a deeper, timeless reality. Some philosophical traditions find this idea of an eternal, self-existing cosmos more coherent than one requiring a creation. Ancient Greek philosophers debated whether the universe was eternal, and modern cyclic models like the Big Bounce offer a scientific vision of an endless cycle of expansion and contraction, with no true beginning or end. The Multiverse Hypothesis takes this further, suggesting our entire cosmos is just one bubble in an infinite, eternally inflating meta-universe, making the question of a single beginning obsolete. These are not just abstract puzzles, they force us to confront our place in the cosmos. We are temporary congregations of atoms, granted a brief moment of consciousness to look up and wonder about our origins. The awe we feel when contemplating the cosmic microwave background or the vastness of galactic filaments is a profound human experience, one that has driven both scientific discovery and spiritual reflection for millennia. This quest for understanding, this need to trace the echoes back to their source, is perhaps the most defining trait of our species. We are the universe become self-aware, trying to piece together its own forgotten childhood. And in that ongoing search, the line between a scientific question and a philosophical one begins to blur, revealing that the deepest mysteries of the cosmos are inextricably linked to the deepest mysteries of our own existence. That single point of infinite density was not located anywhere in the cosmos because it was the cosmos. This is perhaps the most common misconception about the Big Bang. We are conditioned by movies and language to picture a colossal bomb detonating in a dark, empty void, scattering galaxies like shrapnel into a pre-existing space. The reality is far stranger. The Big Bang was not an explosion in space, but an explosion of space. It did not happen at a single location you could point to. It happened everywhere at once. Every part of our observable universe, every distant galaxy, and the space between them was once compressed into that initial singularity. When we say the universe is expanding, we mean that the very fabric of space-time is stretching, carrying galaxies along with it. A useful analogy is a loaf of raisin bread dough as it rises. Each raisin represents a galaxy. As the dough expands, every raisin moves away from every other raisin. There is no center to the expansion on the surface of the dough. The raisins are all simply getting farther apart as the entire loaf grows. Our universe is like that, but in 3 dimensions. This also answers the puzzling question of what the universe is expanding into. It is not expanding into anything. There is no outside. It is all there is, and it is simply getting larger, like the surface of an inflating balloon. Another persistent myth involves the nature of before. People often ask what happened before the Big Bang, but if time itself began with that event, the question may be meaningless. Asking what came before the Big Bang is like asking what is north of the North Pole. The concept of before requires time to exist, and our best models indicate time started then. This does not inherently contradict religious beliefs, as many see the moment of creation described by science as the mechanism through which a divine act was performed. Science explores the how, while philosophy and religion often explore the why. Popular media often gets this wrong, depicting the Big Bang as a flash of light in a black emptiness, reinforcing the idea of a central point. In truth, if you could have been present at the beginning, you would not have been able to look out at the explosion because you would have been inside it, and every direction you looked would have been a blinding, solid wall of energy. So the next time you look up at the night sky, consider this. You are not on the outskirts of an expanding debris field. You are at the center of your own observable universe, just like every other point in the cosmos. The echo of that first moment is not a receding sound from a distant location, but the stretching of the very stage upon which we all stand. The silent hunt for dark matter is about to enter its most promising era. Deep underground, in abandoned gold mines and beneath mountains, a new generation of detectors waits in profound darkness and cold. These experiments, with names like LUX Zeppelin and Darwin, are engineering marvels designed to sense the unimaginably rare collision between a dark matter particle and the nucleus of a xenon atom. Researchers predict that within the next decade, one of these ultrasensitive devices may finally record that elusive tremor, identifying the substance that forms the cosmic skeleton. Meanwhile, the Vera Rubin Observatory, with its colossal 3.2 billion pixel camera, will soon begin a 10-year survey of the entire southern sky. It will not look for dark matter directly, but will watch for its gravitational effects, mapping the subtle distortions of billions of galaxies to trace the invisible web with unprecedented detail. This vast digital sky will act as a forensic chart of dark matter's influence, potentially revealing its distribution with such precision that we could finally infer its fundamental properties. The Square Kilometre Array, a network of thousands of radio telescopes spanning 2 continents, will listen to the cosmic dawn, probing the universe's first stars and galaxies. Its observations could uncover how dark matter shaped the very first structures, testing whether it interacts with itself in ways we have never considered. These colossal projects are not solo endeavors, but massive international partnerships, uniting thousands of scientists across the globe in a shared quest. The pursuit of dark energy is equally ambitious. The Euclid Space Telescope and the Dark Energy Spectroscopic Instrument are meticulously measuring the universe's expansion history, searching for any slight change in the strength of dark energy over billions of years. Is it truly a constant force, as Einstein's cosmological constant suggests, or is it a dynamic field that has evolved? The answer will lock in the universe's ultimate fate, deciding between a cold, eternal expansion or a more dramatic finale. On the theoretical front, the search for quantum gravity is pushing mathematics to its limits. While we may never build a collider powerful enough to recreate Planck energy, scientists are devising ingenious indirect tests. Precise measurements of the cosmic microwave background's polarization could yet reveal the imprint of primordial gravitational waves, a direct signal from inflation that would also probe the quantum nature of gravity. Other researchers are studying the aftermath of black hole mergers, looking for any subtle deviations in the gravitational wave signals that might hint at the granular structure of spacetime predicted by loop quantum gravity. Leading cosmologists suggest that the next breakthrough will likely come from a surprising correlation, a piece of data that does not fit any existing model. It might be an anomalous galaxy that formed too early, a strange pattern in the neutrino background, or a statistical fluke in the cosmic web that points toward entirely new physics. Each of these potential discoveries carries the power to rewrite our cosmic story. Confirming the Inflaton field would tell us what fueled the universe's birth. Identifying a dark matter particle would reveal 95% of the cosmos we have never seen. Understanding dark energy would tell us how everything will end. The journey to trace the echoes of the first explosion is accelerating, driven by a new suite of eyes and ears trained on the sky, and by the enduring human need to understand where we came from and where we are going. You do not need a PhD to help classify distant galaxies. Projects like Galaxy Zoo have harnessed the power of curious minds around the world, inviting anyone with an internet connection to become a cosmic explorer. By looking at images from powerful telescopes, volunteers have helped scientists categorize millions of galaxies, spotting rare collisions and strange structures that computer algorithms might have missed. This is citizen science in action, a collaborative effort where public participation directly fuels discovery. In fact, amateur astronomers and dedicated volunteers have made genuine contributions, sometimes identifying a new type of galaxy or a never-before-seen celestial object. The story of the universe is not just for professionals, it is a story we can all help to write. Beyond classifying galaxies, you can follow the raw data streams from missions like the James Webb Space Telescope as they are released, or join projects that search for distant planets or track near-Earth asteroids. Local astronomy clubs offer a chance to peer through a telescope with your own eyes, to see the rings of Saturn or the haze of a distant nebula, connecting you directly to the cosmos above. This engagement creates a vital bridge between the public and the scientific community. Your curiosity and your voice help advocate for the funding of ambitious missions and the teaching of science in schools, ensuring that the next generation of explorers can continue this grand pursuit. The quest to understand the first explosion is a human one driven by our shared wonder. So go outside on a clear night, look up, and let your own questions about the stars begin. Your journey into the cosmos is just one small step away. Our journey through the echoes of creation has revealed a universe both magnificent and mysterious. We have traced the arc from the first hot, dense state, its afterglow still whispering to us from every corner of the sky, to the invisible scaffolds of dark matter that sculpted the cosmic web. We have confronted the accelerating push of dark energy, a force dictating a future of cold, silent expansion. These are not just abstract ideas, they are the foundational chapters of our cosmic story, written in the oldest light and the motions of the galaxies. Yet for every profound insight, a deeper question emerges. We stand at a frontier where our physics breaks down, where the nature of time itself blurs, and where 95% of the cosmos remains hidden from our view. This is the beautiful paradox of scientific inquiry. The more we uncover, the more we recognize the vastness of our ignorance. Our drive to comprehend these echoes is a testament to a fundamental human need to understand our place within this grand tapestry. As Carl Sagan so eloquently reminded us, we are a way for the cosmos to know itself. The story of the first explosion is our story too, written in the atoms forged in long-dead stars and propelled by a curiosity that reaches for the horizon of knowledge. The search is far from over. It is an invitation. Keep questioning, keep looking up at the stars, and never lose your sense of wonder. If you want to continue exploring the deepest mysteries of space and time with us, subscribe for more journeys to the edge of